Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to talk about orthogonal and orthonormal vectors. And finally, I would say, it depends on your background and such, but probably it's up to this point, you probably have at least been exposed to most of the concepts in other classes that we've covered up to this point. Here, I think we're going to get to something that you may have seen, but you may not have seen. So we're going to kind of chart new ground a little bit. The first thing I want to do is recall, or have you recall, that the vector A, when we dot it in to the vector B, you can write it a couple of different ways, but one way to write it is the magnitude of A times the magnitude of B times the cosine of the angle between. So these are multiplications in between there, right? And just to give you a picture, we've done this before a couple times, but here is vector B, here is vector A, like this, and this is the angle between them. And so when we take AB cosine theta, we're taking the A vector, we're projecting it in the direction of B, and then we're multiplying that length, that projected length, times B. That's what this concept of a dot product is really doing. But we can rearrange that. This is an equation like any other equation, and we can rearrange it. So if we rearrange it to solve for cosine of theta, then what we're going to get is A dot B, and we can divide by the magnitude of A times the magnitude of B. All right, so what this is telling us is that if you would like to calculate the angle between two vectors, then all you have to do is take their dot product. That'll give you a number in the numerator, and then you find the magnitude of A and the magnitude of B separately, multiply them together, and then take the division, and you got it. So this is giving you the angle between any two vectors. Right? So this is important. This is a very useful thing because many times you will be given vector A, vector B, and you want to know what's the angle between them. Is it 30 degrees, is it 40 degrees, is it 67 degrees, whatever. So in that case, you find the dot product, you find the magnitude of the individual vectors, follow that formula, and then you can calculate the angle between these two vectors, A and B. So hang on to this because we're going to do a problem in a few minutes that's going to use that. Now the second thing I want to talk about is the concept of orthogonal vectors. Believe me, it has a very complicated sounding name, just like lots of things in higher math, but really they're very easy to understand. Orthogonal basically just means 90 degrees between the vectors. So the vectors are perpendicular to one another. That's what 90-degree angle is, right? It's perpendicular. So orthogonal vectors, I'll just say here, is 90 degrees between vectors. That's the concept of orthogonality. You could replace this word with perpendicular or 90 degrees, and then it would basically be the same thing. So if I wanted to draw a picture of that, if I had vector B, and if I drew vector A exactly like this, with a 90-degree angle there, these two vectors A and B, notice they have different lengths. A and B are different lengths, but they're orthogonal to one another because they're 90 degrees. They're perpendicular to one another. So sometimes you may be given two vectors and the question might say, are these vectors orthogonal? Are these vectors orthogonal to one another? It just means, are these vectors perpendicular to one another? That's what it basically means. How would you figure that out? I mean, if I drew it, you might be able to figure it out, but what if I don't draw it? What if I just give you the vectors and I give you the components, the I, J, K components of the vectors? How would you figure out if they're orthogonal? Well, what you could do is use what we just figured out up here. We could calculate the angle between vector A and B, and if we get 90 degrees, then we can say that they're orthogonal to one another. So, for instance, if theta is equal to 90 degrees, then cosine of theta, or 90 degrees, is going to be what? Cosine of 90 degrees is 0. All right? And so if we go back up to our definition of the dot product, if there really is a 90-degree angle between these vectors, this term is going to be 0. So that means the dot product is going to be 0 when the angle between them is 90 degrees. So what that means is A vector dotted with B vector is 0, which means that A and B are orthogonal. So in other words, you don't even have to really calculate the angle between them. If you have two vectors, A and B, and you know we've done the dot product several times now. We go back and look at the previous couple sections. We were calculating the dot product at least 4 or 5 times. All right. If you calculate the dot product between two vectors and you get 0, then the only way that that can happen is if the angle between them is 90 degrees, because that's driving this term to zero. There's no way that this term can be zero, because that would mean one of your vectors has zero length. Who cares about a case when one of your vectors is zero? I mean, that's a trivial case. We're not concerned with that. Obviously, this can never be zero, otherwise you have no vector at all. So these can never really be zero. So the only time that you can get a dot product of zero is if the angle makes the cosine drive to zero, which means 90 degrees. So that's a very important test for orthogonality, or for the angle between two vectors to be 90 degrees. Take the dot product, see if it's zero. And if it is, then you've got an orthogonal pair of vectors. So keep that in your back pocket. Remember that, because we're going to use that in a few minutes. All right. Now also, I want you to remember, I'll draw another little line here, or recall, I should say, from a couple of sections ago, that we're going to recall that we can define a unit vector in the A direction, in the direction of vector A. And all we're going to do is we're going to take that vector and we're going to divide by its magnitude. This is finding a unit vector in the A direction. Now, we said that this is finding a unit vector, but another way of saying what we're doing here is we are normalizing the vector A. That's another way of saying the same thing. I'm trying to introduce the term normalizing. If you ever read in a textbook or some other book or whatever, physics book, math book, whatever, and they're talking about normalizing something, or hey, we're going to take this number, we're going to normalize it. We're going to take this vector, we're going to normalize it. The word normalize it means divide, usually means divide by something to make the magnitude 1, to make it equal to 1, basically, a unit length. All right? So the process of normalization is when we take this vector, divide by its magnitude, so we get a new vector in the same direction, but now its length is 1. That process is called normalization. The reason that we care about that is because, the reason I'm introducing that, is because I'm going to introduce a concept called orthonormal vectors. Orthonormal vectors, and that is orthogonal vectors that all have length equal to 1. All right, so it's a very subtle distinction, but you need to understand it, because when we do calculations, you need to know what you're doing. Orthonormal vectors are vectors that are 90 degrees perpendicular. That means orthogonal. So they're orthogonal vectors, right? And all the vectors that you're interested in, let's say we had two vectors we were comparing. The length of each of those vectors are also unit vectors, which means that the length is 1. So the word orthonormal is a composition of two words. The ortho means orthogonal. That means 90 degrees between the vectors. The normal means to normalize, which means the vectors have length 1. So when you think, that's the way to remember it. So orthonormal means orthogonal vectors, 90 degrees between them, length of each of those vectors equal to 1. Now, what is the most famous orthonormal set of vectors that you know of? The most famous set of orthonormal vectors that you can know of, even though you may not realize it right now, is, let's say, the I unit vector and the J unit vector. When you think about it, when you draw it like this, the I unit vector is pointed this way, and the J unit vector is pointed this way. By definition, the I hat vector has a length of 1. By definition, the J hat vector has a length of 1. And also by definition, I hat points along X and J hat points along Y. Because we always know X and Y are 90 degrees separated, we know that I and J are 90 degrees apart, always. Okay, by definition. We know that their lengths are 1. So they're orthogonal, they're also normalized to a length of 1. So I and J are an orthonormal set of vectors. Also, by extension, I, J, and K, meaning X, Y, and Z, that's also an orthonormal set of vectors. All right, because X, or I hat, is perpendicular to the other two vectors, Y and Z, or J and K. K is perpendicular to the other two unit vectors, I and J. So every vector in that orthonormal set, I, J, K, is perpendicular to the other two vectors, and all of those vectors have a length of 1. That makes them an orthonormal set. So that's the distinction. When you have an orthogonal set of vectors, notice A and B are different lengths here. it doesn't matter what their length is. If they're 90 degrees, they're always orthogonal. But if they're orthogonal and they all have a length of 1, we call it an orthonormal set. All right, very, very important, because as we get into vector spaces later on, we're going to be, I don't want to give too much away without confusing you, but basically we're going to be transforming from ijk to some other orthonormal set a lot of times to describe our vectors, and we get into more complicated vector spaces. So the concept of orthogonality and orthonormal vectors is very important. All right, so let's forget about these definitions for a minute and let's solve a couple of real problems, because this concept really looks confusing, but it's not too much. What if we want to find the angle between u and v, between vectors u and v? So here we are going back to our straight concept where we have a vector with these components and another vector with these components. All right, so I know the x, y, and z component of vector u. I know the x, y, and z vector of vector v. And I want to figure out what is the angle between these vectors. Well, clearly I could try to plot it and all that, but that's kind of confusing. So what we want to do is use this definition up here. We want to figure out the angle between the vectors by this definition here. So what I'm going to do is note that cosine of the angle between these vectors is, in this case, u dot v divided by the magnitude of u multiplied by the magnitude of v. That's basically what it's equal to. All right, now let's figure out what this is. So u dot v, here's u and here's v. How do we dot them together? Well, we take the x components and multiply them together, give you 1, plus the y components multiplied together gives you 0, plus the z components multiplied together also gives you 0. And on the bottom, we need to multiply the magnitude of u and the magnitude of v. So we actually can't do much with this right now, so let's take a little aside and let's figure out what's the magnitude of u. Well, you should know by now that the magnitude of u is the squares of each of the components. So here's 1 squared, 0 squared, 1 squared. We have the square root, and so we're going to get the square root of 2 here. And you should know by now that that's 1.41 if you stick it in a calculator. You don't have to represent it as a decimal. You could just use it in radical form, but we'll just leave it like that for now. And then the magnitude of v shouldn't be a huge surprise that it's the same answer, 1, 1, and 0. So it's going to be 1 squared, and 0 squared, which also gives us a square root of 2, which is also 1.41, like that. So what we can do then on the bottom here, this is the dot product of these two vectors. On the bottom, we now know that the magnitude of u is 1.41, and the magnitude of v is also 1.41. So what we end up getting is 1 divided by these two guys multiplied together. We're going to end up with 0.50, or pretty darn close to 0.50. So what we have figured out as a result of this is that the cosine of the angle between these vectors is 0.50. And so the angle, whenever you take the inverse cosine of that, you're going to get 60 degrees. Now you would never be able to figure out by looking at this that the angle between these vectors is 60 degrees. You're just not going to be able to visualize that. If you can, then awesome for you, but 99.9% of the rest of us are never going to be able to visualize in three-dimensional space where this points and where this points and understand that it's 60 degrees. So we need to be able to apply the definitions in order to get there. So we dot the vectors together, right? That's what we get on top. We take the magnitude of the first one, magnitude of the second one. In this case, the magnitude of these vectors happen to be exactly the same, but in general, they won't be. Then we get what the cosine of that angle is equal to. We invert the cosine or take the inverse cosine, and we get 60 degrees. So let's do that whole process again for another pair of vectors where the magnitudes are not going to be exactly the same. So let's say vector A is 2, 1, 2. So x, y, z for vector A. Vector B, 1, 1, 0. That's vector B. And we want to apply the exact same thing. So we're going to recall that cosine of the angle between these vectors is A dot B over magnitude of A, magnitude of B. All right, so first let's go and calculate magnitude of A and magnitude of B. So magnitude of A is the square root of these components squared, 2 squared plus 1 squared plus 2 squared. So this will be 4, this will be 4, that gives you 8. This will be another one, which will be 9. And so we'll have the square root of 9, which as you all know is 3. All right? And then the magnitude of the b vector is very similarly computed, 1, 1, 0, so it would be 1 squared, 0 squared. So this is 2. So this is the square root of 2, which is 1.41. A bunch of decimals after that, but we'll just leave it at 1.41. So now we can plug what we know into this guy. Cosine of theta is equal to a dot b. Now we're in a position to directly calculate a dot b because we have the components right here. So what we can do is say that on the top we're going to have a dot b, which is going to be 2 times 1 is 2. 1 times 1 is 1. 2 times 0 is 0. That's what goes in the numerator. This is the dot product of those vectors. On the bottom we'll have 3 times 1.41. So on the top we will have 3 over 3, 1.41. And so when we get the answer there, on the right-hand side, it would be 0.71. I'm truncating some decimals, but that's basically what it is. So cosine of the angle between these vectors is 0.71. So the angle between these vectors, when you take the inverse cosine, you get 44.8 degrees. Again, you're not going to be able to visualize that it's 44.8 degrees by looking at this. You're just not going to be able to. So you apply the definition. You take the dot product of the two vectors. We know how to do that in terms of components. That's why you get the numerator. The bottom is given from the magnitudes of the vectors, and then we do the inverse cosine there. All right, so far what we've done is we've just applied this definition. This definition right here. Anytime we want to find the angle between two vectors, we just follow the definition here, inverse cosine, we get the angle between two vectors. But now what I want to do is a problem which is a very common problem, by the way, where I give you some vectors and I ask you, are these vectors orthogonal or are they orthonormal? Okay, are they orthonormal is a little bit more common usually. And remember, to find out if vectors are orthonormal, there's two parts of it. First part is they have to be orthogonal vectors, which means they have to be 90 degrees apart. All of the vectors that you're comparing have to be 90 degrees apart, just like x, y, and z are all 90 degrees with respect to all the other vectors in that set of vectors. And all of the vectors have to have length of 1. Both of those conditions have to be true in order for it to be called an orthonormal set of vectors. All right, so let's go move to a blank board here. And let me show you how you might be asked this on a test. So you might be asked, is the set of vectors u1, u2, u3 an orthonormal set? Question mark. Now, of course, you don't know what u1 and u2 and u3 are until I tell you. So let me write that down right here. u1 is equal to the vector 2/3, negative 2/3, 1/3. u2 is equal to the vector 1/3, 2/3, 2/3. And u3 is the vector 2/3, 1/3, negative 2/3. So here, you understand the question. I have three vectors, u1, u2, u3. So they're pointed, each vector is pointed in space in a certain direction and has a certain magnitude. Question is, are they an orthonormal set? So whenever you're comparing vectors to see if they're orthonormal set, typically you'll see it in curly braces. That just means, is this list of vectors orthonormal? And that means two things. It means that all of these vectors have to have a length of 1. Every single one does, and if they don't all have a length of 1, they're not orthonormal. All right? Second part is, these vectors have to all be perpendicular to the other two vectors. That means this vector has to be 90 degrees between this one and this one. If you compare this to this, there needs to be 90 degrees, and there needs to be 90 degrees between this one and this one. And then you move to the middle vector. This vector needs to be 90 degrees between this one and this one, and then the third vector needs to be 90 degrees between this one and this one. If you think of x, y, z, it makes a little more sense. You have, x, y, and z. Each of those vectors is perpendicular or 90 degrees to the other two vectors in that set. All right, so we need to prove that though, and we have fractions and other junk going around that's going to make it a little bit more difficult, but it's not going to be hard. Let's do the first part. Let's just see what the length of u1 is. Well, it's going to be the square root of 2/3 squared plus negative 2/3 squared plus 1/3 squared. And inside the radical, I'm going to have, here's 4/9. Here, you square this, that's going to be also 4/9. And you square this, it's going to be 1/9. So I think you guys can realize that this is going to be 4 plus 4 is 8 plus 1 is 9, so it's 9/9, which is obviously 1. You take the square root, you're going to get 1. What this means is the length of this first vector is actually 1, which is what we said it has to be in order for this to be an orthonormal set. All right? Now, vector number 2, let's check that one out. Vector 2 is here. 1/3 square it plus 2/3 square it plus 2/3 square it. So what I'm going to have over here is 1/9, 4/9, 4/9 from here. Again, 4 plus 4 is 8 plus 1 is 9, 9/9. This is obviously a length of 1. So vector number 2 has a length of 1. Now let's take a look at vector U3. I give you a cookie if you can guess that it's also going to be a length of 1, but let's check it out. So here we have 2/3. So what we're going to have is 2/3 squared plus 1/3 squared plus negative 2/3 squared. And then in here, we'll have 4/9 again. 1/9 here, 4/9 here. No surprise, 9/9. Again, length of 1. So, because of the way we've constructed this set of vectors, each one of them has a length of 1. So, all that says at this point is that each one of these vectors are unit vectors, which means they have a length of 1. We haven't done anything regarding where they're pointing yet. All right? So, let's do the second part of this guy and figure out, is this vector perpendicular to this one and this one? All right, let's tackle that first. So how do we figure that out? Well, we talked about that before. We said if you ever want to figure out if something's 90 degrees separated, two vectors are 90 degrees separated, you just take their dot product and you should get 0. That tells you that these two vectors in question are orthogonal, or which means 90 degrees from one another. So let's take vector u1 and dot it with u2. All right, so here's vector u1 dotted with u2. We're going to multiply the x component, so 2/3 times 1/3 is going to give me 2/9. Okay, this multiplied with this, again, we're calculating the dot product, is negative 2/3 times 2/3, so we'll have a negative 4/9. And then here, we'll have 1/3 times 2/3, which will give us 2/9. And then whenever I add these together, I have 2 minus 4 plus 2. I'm going to get 0/9, which is basically going to give me 0. All right, so that gives me 0. So what this says is vector u1 is orthogonal, or is 90 degrees separated, or 90 degrees angle between vector u2. So this vector is 90 degrees apart from this one. Let's check and see this one compared to u3, because remember, for the whole set to be orthonormal, all of the vectors have to be 90 degrees from all of the other vectors. So let's check u1 dotted with u3. So in that case, 2/3 times 2/3 is going to give me 4/9. And then here, negative 2/3 times 1/3 will give me negative 2/9. And then 1/3 times negative 2/3, again, is going to give me negative 2/9. 4 minus 2 gives me 0/9, which gives me 0. So what we've said up to now is that u1 is perpendicular to this and this. And to be rigorous about it, to be totally, absolutely truthful, we need to go and compare every vector to each of the other two vectors. So we've done this one compared to this one and this one. Now let's go to the middle and compare it to its adjacent vectors, just to be tidy about it. And so now what we need to look and say, what is u2 dotted with u1? So we would be basically saying, what is this dotted with this? But when you think about it, we've already calculated what u1 dot u2 is, this one into this one. So if we're going backwards, it's exactly the same math. This times this, plus this times this, plus this times this. We've already done that calculation. So I'll put 0 without actually showing anything, because when you dot the vectors, you can flip the order of them and you're going to get the same result. But we actually have not done We've done this one compared to this one. Let's do this one compared to this one. We haven't done that one yet. U2 dot U3. We haven't done that one yet. So we'll look at the x components. 1/3 times 2/3 is 1/9. Oops, 2/9. 2/9. 1/3 times 2/3. And then we have 2/3 times 1/3. Again, we'll have 2/9. And at the end, we'll have 2/3 times negative 2/3, which gives negative 4/9. 2 plus 2 minus 4 gives us 0/9, which gives us 0. All right, so we have done, for the vector 2, we've compared this one to this one and this one to this one. Now, to be rigorous about it, let's compare 3 to 1 and 3 to 2. So U3 dot U1, we do that calculation, no problem, but this is going to be exactly the same as U1 dot U3 because the math is symmetric, so we know that that's going to be 0. We don't have to show anything. And U3 dot with U2, we've already done U2 dot U3, which we got 0. The math is symmetric, so we don't have to show all that again. What we get is that no matter what vector we pick, when we compare it to the other two vectors, we always get a dot product of 0. Which means that every vector has a 90-degree angle between it and both of the other vectors. So the 90-degree part of it is proved by all of these dot products. We have already proved that each of these vectors has a length of 1, so we say, yes, this is an orthonormal set. Two parts of it. First part, they all have to have a length of 1. Second part, all the vectors are orthogonal, or 90 degrees separated to the other ones. And that is all I have for this section. It's a lot of important material, foundational material that we'll be using as we go on through the class. We started out talking about the dot product and how to calculate the angle between two vectors. We use that to define a rule to figure out when two vectors are 90 degrees separated, 90 degrees apart. And then we learned about the concept of orthogonality. Orthogonality just means they're 90 degrees apart. Orthonormal means that they're 90 degrees apart and all the vectors have a length of 1. And so we've done a couple of examples to show how that's done. Make sure you understand this material. It should be crystal clear with these examples. And then follow me on to the next section where we will continue building our skills step by step in linear algebra.